will be your moderator. I'll be your moderator today. Please, to keep the quality of the sound functional during the meeting, please mute yourself if you are not sharing. And if you have any comments or question during the session, please type it. So today we have Mark Panning, and he's going to be talking about planetary geophysics. Uh, Mark Panning is a seismologist at the Jet Propulsion Laboratory at California Institute of Technology, and we are so glad to have you today, Mark Panning. You have the floor.
Thank you. I am unmuted, right? Yes, great. I was asked to kind of talk about, what it's like as a professional geophysicist, and I just like to point out by saying I followed a really weird career route, and I've got a kind of strange job for a geophysicist. There aren't many of us who get to work on other planets. But that's what I get to do, and so I'll kind of talk about how that works and what kind of things I do. First, what kind of projects am I involved in? So I work at Jet Propulsion Laboratory, which is a NASA center in California, in Southern California, the Jet Propulsion Laboratory focuses on robotic exploration of other planets. That's the whole point of JPL. And everybody who works at JPL, it's mainly engineers, but there are a few scientists as well. We're about 10% scientists, and it's our job to come up with the science to drive the missions that the engineers build to go to other planets. And so everybody gets involved in multiple projects. It's just the way it works. And so I have a handful of projects I'm working on regularly. So I'm the project scientist for the InSight mission that's currently operating on Mars. I'm going to talk about that in a little bit. Project scientist means that I'm not in charge, but I coordinate with all the scientists working across the world, actually. And coordinate them and work together to make sure we're getting good science out of the mission. Also the principal investigator, which is kind of more like being in charge for the far side seismic suite. So we're building a seismometer package to go to the far side of the moon and land there in 2024 or 2025. And I'm also working on the Dragonfly mission. I'm just a co-investigator on that. I'm just helping out, thinking about the science that we can do with the seismometer that's flying on this Dragonfly mission, which is a really cool mission that involves basically flying a drone on Titan, which is a moon of Saturn. And then meanwhile, I always have lots of background things where you're trying to build up stuff for the future. So thinking about seismometers on Europa or Enceladus, which are other icy moons, kind of like Titan, but smaller. And thinking of other ways to do things on the moon aside from what we're already trying to do. And so on an actual day-to-day basis, number one, I don't spend as much time actually looking at data. I used to spend a lot of time looking at data. Now it's more trying to get projects together and make sure that things are in place for other people to look at the data and do great things with it. That's a big part of it. And basically coordinating all the science activities that are happening, making sure that good science is happening. JPL is not a school, so I don't get to directly have students or grad students, but I can bring in postdocs after people have finished their PhD, or work with interns that are undergraduate or graduate students. So there's still a chance to work with education, and a lot of time is spent trying to think about what's the next project. So coming up with ideas and proposing them to try to make them happen. So first I wanted to talk a little bit about InSight. That's the mission on Mars. And if people have questions during this time, raising hands or things like that, I don't mind being interrupted, and I'm going to leave time for questions afterwards too, but I really don't mind being interrupted. So if people want to raise hands or put things in chat, I'm happy to talk. So number one, the first thing I got to say about InSight Science is that there's a giant science team, and it spans the globe. We have lots of people just all over the place that are working on this, and so everything I'm talking about is the work of really hundreds of people. So number one, sorry, my slide's not advancing. So why are we doing InSight? Why are we doing seismology on Mars? It's a reasonable question to ask. But what we're trying to do is basically take the basic scientific knowledge gathering approach that we used on Earth and apply it to another planetary body. And it's, the basic questions, the structure, how thick's the crust, how big and how dense is the core, what's happening in the mantle, where do quakes happen, and ask these basic questions. And these were the same basic questions that drove a lot of the experiments that were put up by the Apollo missions in the 70s on the moon. And we're doing this all trying to do this from one spot on the surface of Mars. And so basically all of these bodies, Earth, the moon, Mars, Mercury and Venus, are all these rocky bodies that have started out pretty similarly, but have followed different paths for a variety of reasons. And so if we want to understand why rocky bodies do what they do, then we got to look at more than just the Earth. And so in order to do that, we've got our lander, which landed in late 2018, November of 2018. And we have three main instruments that we work on it. And I don't remember what all the acronyms stand for, so I won't spell them all out. NASA and space missions, they love acronyms. So acronyms are everywhere, and I don't always remember what they are. But the seismometer is what I work with and what I focus on. And that's sitting here underneath this kind of pie plate looking thing here. That's our wind and thermal shield. We also do radio science with X-band antennas that communicate back to Earth. And there's this last thing called the heat flow and physical properties package, HP cubed, that was designed to drill down, hammer itself down up to 5 meters and measure temperature a profile, which give us heat flow. That one actually didn't work as designed, so I'll get back to that too. But in order to do this, we also have a lot of instruments to support those major instruments. And so we also have this arm that's designed to deploy it, but also has cameras and a scoop. We've got wind measurements, we've got a magnetometer, we've got a pressure sensor, and other cameras and things, and all of these things actually have produced science that has been a good output of our mission. But originally they were designed to support things like the seismometer, which is really sensitive to lots of things. So we want to know what the wind and the pressure and the magnetic signals are doing. We video here on the right is 70 sols, which is a day on Earth and a day on Mars, rather. And a day on Mars is just a little bit longer than a day on Earth. This is just pictures taken from our context camera, which is underneath the lander with a fisheye lens, and it's showing everything. So we're putting the seismometer out there on the ground, a little over 1 meter away. And then eventually we're gonna let the tether go so it's on the ground, so it's not blowing in the wind. And then we do some things where we're trying to open up this little loop here so we're not directly connected in with the tether. And this took us like 2 weeks to figure out how to get that thing going, because the arm wouldn't catch the hook and it was very difficult. It's kind of like one of those carnival skill crane things. I don't know if those are everywhere, but it was challenging. And then we put this wind and thermal shield over the top and adjust it and finally release it. And 70 sols in, we have a seismometer functioning on the surface of Mars where we want it to be. If we wanted to install a seismometer anywhere on Earth, it would take us maybe a couple hours. No, it took us 2.5 months on Mars because we had to do it by a robot and communicate, take a picture, wait a day for the pictures to come back, wait a day to send the commands up, and everything just took forever. But that's what it takes. We had a great seismometer on the surface of Mars. Here's some pictures of trying to open up that loop, which I talked about. That's hard. And then we recorded. So this is through a couple weeks ago. This is actually a few weeks ago. I didn't update this recently. This was that's not, I put this together and I didn't update it today. I apologize, but this is a way of displaying all our data in the mission to date. And basically each line going across is a sol on Mars. The gray lines are sunrise and sunset, and the warm colors are times when the seismometer was very noisy. And the kind of purpley colors are when the seismometer was very quiet. So we had quiet times in the evening in the first part of the mission, and we recorded lots of quakes. That's all the signals on here. And then we went through the dust storm season, and it was noisy all through the day, and we recorded almost nothing. And then we wrapped around to the next Mars year, and we started getting the quiet evenings again. If I continued this through to today, you'd see that the quiet evenings have been continuing, and then they're on their way down. We actually just had a dust storm 2 weeks ago that made the atmosphere so dusty that our solar panels couldn't get enough energy to keep us going how we wanted to, and we went into something called safe mode, and we pulled out of that, and we're now turning the instruments back on. But you know, running solar power on a dusty place like Mars is hard. But we were expecting to see Mars quakes, but they've never been seen before. The Viking missions in the 70s included seismometers, but weren't able to actually convincingly record any Mars quakes. So we didn't know exactly what we were going to see, but we did start seeing Mars quakes that had nice PNS waves. This is our first big one. When I say big, it's magnitude 3.7, which is not a very big earthquake, but it's a pretty big Mars quake, because Mars is much quieter than the Earth. But you could see that we could pick out PNS waves. But there's also weird features in the seismic records called glitches. This is because temperature is changing so much on Mars, because we couldn't put in a perfect station, that everything's cracking and popping, and we see these things all the time, and they mess up our data, but we deal with them. So we started locating events, and one of the interesting things is most of the events we've located, not all of them, but most of them are happening in this place called Cerberus Fossae, which is like an old volcanic area on Mars. But when I say old, it's actually not that old. We know it's been active geologically recently in the last 10 million years. These images from orbit show rock trails that look like they were caused by Mars quakes. And so this was one of the places we were expecting to see quakes, but we didn't know if we would. But it seems like most of the quakes we see are there. This is about 1,500 kilometers away from us. So not very close. And we're seeing magnitude 3 and 4. 1,500 kilometers away on Earth, we would not be able to see quakes that small. But on Earth, no seismic station can be as sensitive as we are, because there's always ocean noise, and there's no ocean noise on Mars. So we get to see more stuff. Over last summer, we finally published most of our key results, that we were able to identify Mars quakes that showed us how thick the crust was, and how big the core is. And from that, we can, by combining with gravity, we can estimate how dense the core is. So it tells us what it's made out of. It's actually not all metallic. There's a lot of light elements in it, more light elements in it than are on the Earth, in the Earth's core, and you know, basic mantle structure. I can talk more about the details of that, but I wanted to leave time for people to talk about other things. So, it has been a challenge. We're a solar-powered mission on Mars, and we don't have a way of cleaning off the solar panels. Some long-lived solar-powered missions on Mars, like the Spirit and Opportunity rovers, they were repeatedly cleaned by dust devils going by. So like a little vortex would go by and pull dust off the panels, and they'd get cleaning. And we thought we were going to get that, but it has never happened for us. So we just get more and more dusty. And we've managed to keep ourselves going longer than we initially thought, by some cleaning activities. We actually dumped dirt on ourselves here. You can see we dumped a little pile of dirt on top of our lander here. But we did that at high wind, and some of that dirt went across the panel to the left here and actually cleaned dust off. So by dumping big sandy chunks that bump off the dust, we were able to actually get quite a bit more energy and keep going a little bit longer. So my other major project is thinking about the moon, and it's this thing called the Farside Seismic Suite, which we're planning on having everything live in this little box here that's on top of a lander that hasn't been decided yet. It'll be a commercial company who's supplying us a lander, and NASA's paying for us to put our box on that lander and land on the far side of the moon in Schrodinger crater, so a place that never sees the Earth. And we will measure from the deck here. The lander is not designed to survive into the lunar night. So on the moon, the night lasts 2 weeks. And so it's really hard to survive through that. The lander's not designed to, but we're going to do it because we're a little box, so we can keep ourselves warm and toasty, and we can just put enough batteries in there that we can continue operating through the night on about 5 watts. So, that's not very much energy. We keep running through the night, measuring through the night, and then we communicate through the day to a relay satellite. And the lander is just dead at that point, and we're functioning on it. And we're looking at a lot of things. So the Apollo missions measured moonquakes, which are really cool, but they were all on the near side because that's where the Apollo missions were, because they had to be able to see back to Earth for communication, et cetera. We're landing over here at Schrodinger crater on the far side, so we don't know if there are how moonquakes are on the far side. They may actually be less. We've never seen them. There are a lot of differences between the near and the far side. If you see the near and the far side of the moon, they actually look very different at the surface. All of those dark spots you see that make the patterns we see on the moon, those are mare. They're not on the far side. And there's a lot of differences because of this whole thing, the moon being tidally locked with us. So we want to know about that. We want to know about the structure at Schrodinger crater. It's actually a relatively young, fresh crater that's got impact melts on the bottom. And so we want to know what the structure of that is. And we want to look at the background noise of the moon, which is really, really quiet because there's no wind or oceans to drive noise. It's only being driven by little tiny meteorite impacts. And if we can measure what that noise level is, we know what the rate of micrometeorite impacts are, which is pretty important for future human habitation on the moon. Moonquakes are weird. This is an hour of seismic data on the Earth or the moon. On the Earth, it looks like just a spike. There's actually all those PNS waves and things like that in there in reality, but on this scale, you don't see it because it's an hour long. But on the moonquake, you just see it bouncing around for an hour. The biggest moonquakes actually vibrate along for 3 or 4 hours. And it's just because the moon is dry and broken up. And so the seismic energy just bounces off everything constantly. And so it's a mess. And the other thing that we were trying to do that wasn't been able to do with Apollo actually had really good seismic instruments, but they had really crappy ability to send that data back. They had to send it in 7-bit data. So it had almost no dynamic range. And most of the small moonquakes look like this, where they're just bouncing up and down by, 1 digital unit. And so they look like a barcode and not a seismogram, and that's really hard to deal with. So we're sending modern instruments with modern digitization. So we're excited about that. We have 2 instruments we're sending to the moon that are actually both the instruments that flew on InSight. So this is the sensitive seismometer, the VBB seismometer. We're actually using a spare instrument from InSight, but we're also flying, that's only going to be 1 component. We'll get 3 components with these SP sensors, which are on little silicon chips that are 1 inch by 1 inch. And then you package those up and get 3 components and measurements from those. It's all put in this box within a box, and with a whole big pile of batteries, so that we can keep running through the night. So that's what we're looking forward to. I don't have any data to talk about yet because it hasn't launched yet and we haven't built it yet. We're starting building it right now, but it's got to be finished by summer of 2023 so that it can launch and sometime in 2024 or maybe 2025. It depends on what the commercial lander is able to do. But so just thinking about how the career path works, once you're in a job like this, and not many people get to work on planets, but there are lots of people that get to work in national lab type settings. And so it's, anytime you're working as a scientist in a lab like that, it's a large part of your job is thinking of the next project. So you're basically trying to bring in money to do projects to keep people at the lab busy. So you have to spend a lot of time working on that sort of stuff. Unlike something in a university, you have to really get hands-on working with engineers for the technology development, which has been a lot of fun. And for me, it's really about thinking about how we can do it in difficult places. As it's a challenge, but everything takes a really long time in planetary science. So InSight is operating on Mars and has been for 3 years, but we started the process. I started getting involved in the process 10 years before that, and the lead of the project, the principal investigator, he started working trying to get seismometers on Mars in the 80s, and it took a long time. Been working on Dragonfly for a long time, and it's still 5 to 6 years away from even launching, and then 13 years away from operating on Titan, because it takes a long time to get there. So have to be thinking about the next project because it takes so long. And that's what I shared. This was like a really quick sort of thing, but I wanted to leave time for people to ask questions, or and I can talk about whatever if you want.
All right, thank you, McFarlane. Thank you for your nice presentation. All right, to the audience, is there anyone who have a question? I have a question, but I think my question will be last. So if you have a question,
Okay.
please unmute yourself and speak.
Good evening, Mr. Mark.
Hello.
Yeah. Okay, I just graduated from the University of Calabar from applied geophysics. And lately I've been looking for where I can further my studies on applied geophysics, either on any scholarship or any school, but I don't have recommendations because the scholarships online and the opportunities to study in other universities come with changing the course of choice. So I don't know, I need some recommendations to study in a good university outside.
Yeah. So there are if you're still a student, there are internship possibilities. So if you can extend, student things, internships are a good way to meet people and have them have recommendations for you.
Okay.
So and this day and age, with COVID being what it is, a lot of internships are totally virtual. So you can do them without having to travel around the world, but still work at internships around the world. So that's one option for getting the recommendations to help you get into other universities.
Okay.
That's the route a lot take. Aside from that, recommendations are important, and I don't want to minimize recommendations, but you can apply without having like big names recommending you or something. You don't need a big name recommendation. It's if you've got somebody who knows you and can really talk about you, that's more important. That it's a good recommendation that really helps. So I don't bring in students anymore because I'm not a professor, but I used to be a professor. I used to teach at the University of Florida. And when I would look at like graduate student applications or things like that, then it didn't matter the name of the person. I just try to see if this person like really just seemed to know the person was describing strengths very well. So yes, I'm not going to deny that a big name can help, but a big name who really knows you. So this is why internships are helpful. But
do you have is there any university you can recommend for me to further my education or do any internship virtually?
So you're saying you're working in applied geophysics.
Yeah.
I mean, so there's certainly there's a I know US universities, and there's a lot of ones that have really great programs in applied geophysics. I don't and spanning the gamut. I mean, you can go like the high prestige ones, which are like, Stanford or something like that, has amazing, but they're great programs down through lots of levels there. Colorado School of Mines has a great program. Lots of the Texas schools, Tulane in New Orleans, and the list is long, and I'm not being exhaustive by any means. But internships, you can, in the applied sorts of fields, there are, you can do internships through private, through companies. They're definitely interested in bringing in interns, and that's really valuable for the applied geophysics route. I don't have a recipe or an answer, but those are some possibilities.
Okay, sir. Thank you so much, Mr. Mark. Thank you very much.
Thank you so much.
So when is the next class?
Say that again?
When is the next class?
The next, are you talking for your program or
I mean the next tech program, the next tech program class like this on Zoom.
Oh, okay. That will be next week. And you see it on our LinkedIn page. All right. So thank you. Is there anyone who has a question again from the audience?
The rest of the kids are muted. I don't know, maybe it's because of data. The rest of them are.
They can reach them. They can unmute themselves rather.
So, sir, how's your day going? Where are you currently?
I have a question, Makani.
Sure.
If I want to do a research on Mars or the Moon, where do I get data to work on? How can I get data?
Yeah, so most of the data we have from Mars and the Moon are all available through the IRIS Data Management Center. I'm not sure how familiar you are with that, but if you go to iris.edu, you can follow the links to the data management center. So all of the InSight data from Mars is available on there. The original data from Viking is not there. You can get that through something called the Planetary Data System, PDS. There's the geoscience node has the data from Viking. The Apollo data will very soon be available from IRIS in a very good format. I've got a postdoc who's working on getting that into the IRIS data management center so everybody can get all of the Apollo data too, and that includes a lot of different kinds of instruments. So the data is free and publicly available. And that's a big thing that NASA pushes, that they want things. The older data takes time because it wasn't originally put in a format that's easily shareable. So that's, that does take time, but just getting the data is, you can get it from IRIS or the Planetary Data System, the PDS. And if you have questions about that, feel free to email me. And you can share the email with others. I'm happy to talk about some of that, but it's actually all publicly available for the most part.
Okay,
thank you so
I'd like to get his email, please.
No problem, I'll share the email with everyone. So I'd also like to ask, if we are going for a graduate studies and we want to major in planetary geophysics, is the undergraduate degree in applied geophysics, is it enough, or do we need to do something else? Do we need other additional skills to be considered, to be competitive? And to offer those, courses, because I know it's not all universities that has a planetary whatever.
Yeah, so I mean, a lot of people come into planetary science things with degrees that aren't really directly about planetary. I mean, so my undergraduate degree was in geology, and I did my grad work on seismology on Earth. Okay. And so, there was, and most of the people I know in the field, most of them started out somewhere else. They started out in physics, or they started out in chemistry, and then started applying whatever they were doing to planetary projects. So it's certainly not, an applied geophysics degree is definitely something that can be applicable to planetary approaches. There's no, working in planetary is, there's not that many of us, and it's kind of a group of oddballs who all came at it in a different way, right? So there's not a path that I could say that everybody took or most people took. You kind of find your way into working on planets because, like as you said, most schools don't have much that where you can get a degree in planetary science or something like that. So you're definitely can get at it in different ways. But I really do recommend, if you're, interested in it, is just look for opportunities for programs, for internships or observer programs or things like that, so you can start meeting people in the field. For instance, Insight, we have an observers program for advanced graduate students, where they can come to our science team meeting. And then before that, we have like an introductory section to talk about the science and connect each person with a mentor that talks about things. And several missions have similar programs. There are summer schools. So JPL does this planetary science summer school, which has been virtual the last few years, where you can basically be involved in planning a fake mission from beginning to end. So like coming up with the concept and figuring out what you need to build and how much that's going to cost and all of that. And so those are a really good way, regardless of what your actual degree is in, to get connected in with people in the planetary science community.
All right, thank you. I also want to ask that, is there a possibility for life on Mars, or what is the main reason, or the main reason behind the research that we are doing on Mars and the Moon? Do we want to go there to to live or something? So what are the reasons for this?
Yeah, so there may have been life on Mars in the past. I don't think it's likely that there's much life there now, although it could be stuff living deep in the subsurface, because there likely is liquid water at some depth on Mars. If you're thinking about life, I think the better places to think about that are the icy moons of Jupiter and Saturn, because they've got lots of liquid water and they're very active. So that's where life could happen. That's one reason why I've always been interested in those. But for Mars and the Moon and all of that, it's for me, it's more about the pure science of understanding how rocky bodies form, why Earth is the way it is, versus how Venus is the way it is. Venus is like, in many ways, exactly like the Earth. It's the exact same size, almost the same chemistry. Everything started out almost exactly the same, but Venus has this really thick, crazy thick carbon dioxide atmosphere, which makes it so hot at the surface that everything melts and it rains acid. Whereas we've got, pretty nice place here on Earth. So, like understanding why things went differently is pretty important in my opinion, and trying to understand, what could happen on other places. And the analogy I always use is like, if you really want to understand the Earth, a doctor doesn't really get really good by going to the same patient over and over again. They go to lots of patients. And so if you want to understand the Earth, you got to look at other planets too. So that's my short take. And of course, big reason is it's, you know, it's exciting to try to go to new places and do new things that are, I mean, you know, I don't have to necessarily come up with a deep reason to say, hey, going to Mars is cool, right? So that's part of it too.
So, do you have, do you know of any internships that we can, you know, that we can join from as a student from Africa or Nigeria, either
Yeah.
online or in person?
Yeah, so like as I said, most internships now are at least, you know, I can say at JPL for certain, we actually aren't allowed to bring in-person interns, and with very few exceptions. You know, if you've got something that you really need to have them in the lab, then you can jump through all sorts of hoops. But and for most interns, we can't bring them on lab, so they have to be virtual. So if you go to JPL has an internship section on their webpage, and individual scientists who are working there will post opportunities there. So that's on the internship scale, and all the NASA centers have their own internship programs. So you can, you know, if you're looking for people who are going to other planets and doing science, the Marshall Space Flight Center for NASA and the Goddard Center, they also bring in interns. It's actually, for bringing in foreign nationals, is easier at JPL than some of those other ones, because JPL is we're not technically NASA. We only work for NASA, but you know, I'm actually not a government employee. I work for the California Institute of Technology, because of the weird way that JPL is structured. So it's easier for us to bring in foreign nationals because we're not government employees. So JPL is a good place to look. But aside from that, lots of individual university professors will advertise them. There are, you know, like, so I would recommend getting on the IRIS mailing list. So iris.edu. If you go to those, you can get on mailing lists, and people will send out opportunities, both for internships and like student opportunities of various types. So that's another good way to find out about them. Yeah. And then, you know, I would recommend Googling the Planetary Science Summer School. I'm not sure how that one works, but that's a JPL one. Yeah, so those are some opportunities. I'm not, you know, I'm not an expert. I don't know all of the ones out there, but those are some places to look, at least as a starting point.
Thank you so much for your answers. It was really helpful. And also, I would like to ask, since you are at Caltech, so are there any opportunities at Caltech, at California State?
Yeah, so, you know, so while I technically work for Caltech, I really work for JPL, so I don't know much details about how things work on campus, but there certainly are lots of internships and things available through individual researchers on campus. I'm not sure if there's a central web page for Caltech where you can see the opportunities. That would be really useful, but I'm not sure. I'm not sure if one exists. I can do some looking and see if I can find one, and I can send them by email to you if I find any kind of central website where you can find them. That's a good question. I wish I had a better answer. But yeah, so, you know, the planetary science, I will follow up with you and send you some websites for Caltech, hopefully, that I can find. I can't guarantee anything, but I don't have anything able to answer you very quickly on that. Sorry.
Fine. Does anyone have a question before we end the meeting?
So how was your day today?
Well, I'm just starting. You know, it's 10:45 in the morning here, and it's on Sunday. So I got, you know, I got up and, you know, worked on a crossword puzzle for a bit. You know, I haven't done much yet today. I do see somebody's hand up.
Please, can you mute yourself and speak?
Yeah. Thank you very much. I didn't really get everything you said.
I'm sorry, I can't hear what you're saying. The sound is really bad.
You mentioned something about the moon being dry. How is that possible?
I missed almost everything you said at the beginning, but I heard at the end you said something about the moon being dry, and how is that possible? I can't hear you very well. It might be better if you type something into chat. Can you hear me?
Yes,
Or
yes.
so I missed the beginning. If you want to put something into chat.
Yes, I can hear you.
Your network is poor, so we can't hear what you said. So please, can you type into the chat box so we can pick your question from there?
So the question about the moon being dry. So we have very good evidence that the moon is relatively dry. It's not that there's no water anywhere on the moon. We you know, you can look at spectroscopy and see that there is some amount of hydrogen and hydroxide on the surface that's likely related to water, and there may be a little bit of ice in some of the permanently shadowed regions. But the fact of the matter is, near the surface anyway, it's a vacuum at the surface, and so water is easy to escape. You know, it'll sublime and then escape to space. But the reason why we know it seismically is because of how crazy the moonquakes are. In order to get those long vibrating trains, if there's any water or ice, any significant amount of water or ice in the material in the top several kilometers of the moon, then the seismic energy attenuates more. It dies out more quickly. That's what water does. And the fact that it's able to bounce around for hours tells us that the moon has to be both very broken up and very dry, so that the energy has lots of stuff to bounce off, but doesn't decay away very quickly. It's really strong evidence of that, but it doesn't mean it's totally dry. There are likely places where you can find water on the moon, and certainly people are thinking about how to take advantage of that for making fuel for rockets, etc. And the second question is, why do we study other planetary bodies? So I kind of talked about that already, but I just really want to emphasize that number one, the reason why I study is because I think it's really interesting and I want to find out about it. I mean, it's knowledge for knowledge's sake. But number two, if you want to understand the Earth, you have to understand why the Earth is the way it is. You have to understand why other planets are different. I think it's really important in terms of understanding how the Earth is the way it is and how it's evolved over time, is to understand how other planets have done it differently. So we have another question that says, speaking of planetary bodies, Elon Musk recreating life on Mars, what's a role in making this possible? I certainly think so. Number one, Elon Musk does work with Jet Propulsion Laboratory on some level. Like when he was trying to think of places to land on Mars, he talked to JPL, because JPL are the people who know how to land on Mars. Until the Chinese managed to land recently, nobody else aside from JPL had successfully landed on Mars. So that's certainly something of interest. In terms of Elon Musk, I think everything we do to better understand Mars and the Moon helps us to be able to establish human habitation there. I don't know how quick any of that's going to happen. I work on robotic exploration because the nice thing about sending a robot to study another planet is you don't have to figure out how to get them back. It's more challenging when you're sending people and you have to keep them safe and then find a way to get them back. And so that's a lot more challenging, but obviously it's exciting. It's real exploration. So I'm happy to see people working on it. It's just for me, it's easier to think of doing things with robots. I think the next question is asking how, when you say how fast can the Moon work, if you're talking about lots of different levels, if you mean how fast can I get the stuff I want to get to the Moon there, as I said, we're trying to finish building everything in the next year or so, and then within 2 to 3 years we'll have our seismometers on the Moon. But in terms of people, that's probably going to take a little bit longer. The politicians were saying 2024 for the US, but in reality they're not on pace to do that. In terms of getting more permanent human habitation, that's going to take time. I think the private companies probably might be able to do it more quickly than governments, but I have a hard time predicting stuff like that. But I will say there's a lot of activity on the Moon right now. NASA is trying to hire commercial vendors to make landings on the Moon once or twice a year, starting this year. Hopefully something will launch. And of course the Chinese are very active and sending missions to the Moon, and the Europeans are talking about it as well. So I think a lot's going to be happening on the Moon in the 2020s. I think it's going to be very active.
Thank you, Makani. It's been a wonderful session. Please, does anyone have a question before we end the meeting? All right, on that account, I think we have come to the end of the webinar. Thank you so much, Makani. It's been a very interesting session.
Thanks.
Yeah. So
thanks so much, sir.
Thanks. It's been fun talking to all of you.
All right. Please, I would like everyone. Please, I would like everyone to turn on that video. Can you please turn on your video so we can take a screenshot? I'll take a screenshot.
It doesn't seem like a lot of the videos are coming on, but
All right, that would
I
do
think
that.
it's just 3 people who are active.
it's Sunday evening. Nobody wants to show their face.
Yeah. Maybe it's because there's no light in their locations too. Somebody.
Nigeria, we don't have good electricity.
This one is generator.
That's
Even
that
me, I'm
does make
using my
it challenging.
Right. Thank you. Thank you so much, McFanny. Get
Thank you so much,
in touch
Makani.
with your mail. Get in touch with you. So I just want to say thank you so much for honoring our invitation. It's
Okay,
pleasure.
thank you for the information you give me.
Thanks. It's been, as I said, it's been a lot of fun talking with all of you. So enjoy the rest of your evening, and I did put my email in the chat. So if people do have questions, I'm happy to talk over email. I may be a little slow at responding sometimes, but I'll try to respond as quickly as possible.
All right. Thank you very much, McFanny.
Yeah.
Thank you. Enjoy the rest of your day.
Yeah. Thank you.
Bye.
Bye.